Now that we have the Heaviside step function at our disposal to handle deleting the past with a Laplace transform, let's go ahead and see what happens when we find the Laplace transform of a shifted function. But remember, to have any hope of success, we have to have our shifted function multiplied by a step function that's shifted the same amount. Okay, so as usual, when you don't have a Laplace transform rule yet, you have to do this by hand using the definition. So we'll calculate the integral from 0 to infinity of e to the minus st times u of t minus a times f of t minus a dt. And to make any progress here, right, we kind of expect that whatever this turns out to be, it will be in terms of the Laplace transform of f. So to have any hope of making the Laplace transform of f show up, inside of f, we have to have just a variable, not a shifted variable. So this is sort of indicating that maybe we should make a substitution. So let's pick a new variable name, maybe, I don't know, how about x? And let's say that x is t minus a. When we calculate dx to do the substitution in this integral, we find that dx is the same as dt, so that's simple enough. So this is the integral. Now we have to adjust the bounds when we do this. So when t is 0, x is minus a, and when t goes to infinity, x also goes to infinity. So up to infinity there. E to the minus s times t, but t is x plus a, right? Because we can rearrange this equation to read x plus a equals t, times u of x times f of x dt. Okay, now u of x is a piecewise function, and we have seen in an example in the past that to deal with a piecewise function, you should break up an integral at the, oh sorry, this should be x here. To deal with a piecewise function in an integral, you should break up the integral at the value where the piecewise function changes. Remember, the step function u of x is 0 when x is negative and 1 when x is greater than or equal to 0. So we need to break this integral up at x equals 0. So we'll go from minus a to 0, e to the minus s times x plus a times u of x, f of x dx, plus the rest of the integral is from 0 up to infinity, e to the minus s times x plus a, u of x times f of x dx. Okay, now in this first integral, for x values from minus a to 0, u of x is 0. So this inside this first integral, u of x makes the whole integrand go away, and so this entire integral is 0. In the second integral, for x values from 0 to infinity, u of x is just 1, so this becomes a 1 right here. And so we get the integral from 0 to infinity of e to the minus s times x plus a times f of x dx. Now this looks like something we have some hope with because the variable inside of f is just this variable that we're integrating with respect to. So this ought to turn into a Laplace transform if only we could deal with this exponential, but we have this sum here, so we can write this exponent as minus sx minus as, and then split the exponential up, so we get integral from 0 to infinity of e to the minus sx times e to the minus as times f of x dx. But this second exponential here doesn't depend on x, so we can move it outside of this integral. So this is e to the minus as times the integral from 0 to infinity of e to the minus sx f of x dx. And this integral is now just the Laplace transform of f. So this is e to the minus as times the Laplace transform of f. And so we're done. We figured out what is the Laplace transform of a function that's shifted and has multiplied by a step. And we got that a shift right in the t world looks like multiplication by an exponential in the s world. Now this is a little confusing because the amount of the shift you might expect, based on analogy with the corresponding Laplace transform law that says multiplication by an exponential in the t world is a shift in the s world, you might expect this to come out to be plus as, but it's actually minus. So you have to be careful to get this minus sign right. If you leave off this minus sign, bad things happen. Another thing that we have to be careful about is we actually made an assumption up here that the shift is way back up here. When we did this shift and we were able to, here it is, we were able to discard this entire first integral. We were assuming that minus a is actually a negative value. But if a itself were negative, minus a would be positive. So, and then we wouldn't be able to just discard this entire first integral because this step function wouldn't be 0. So we actually have to add the condition. We sort of made a subtle assumption here that a has to be positive. So this Laplace transform rule is only true for positive values for a, so that is shifts to the right. Shifts to the left, there's no hope of finding a good Laplace transform rule for shifts to the left, because if you shift a function to the left, some of what that function is gets moved into negative t values, and then the Laplace transform can't see it. So, so for this shift in t, it has to have positive a values.